Good morning, everyone. So let's start with a lab session, which is lab session number 2 for this deep learning course. Can anyone please confirm if they can hear me on the chat? All right, thank you. All right, so before we start with today's lab session, which is going to be about how do you build your neural networks from scratch and how do you train those neural networks. Let's actually jump back to our last session from where we're going to probably cover another topic that we didn't cover last time, which is logistic regression. And once we do that, we're gonna extend the same concepts that we've learned in the last lab session, and then jump into the deep learning side of it, the deep learning world, which is all about neural networks and how do you train them and stuff like that. All right, so if you guys can open your lab sessions from last time, you would have remembered that we did some linear regression stuff on stock predictions, right? And then we use two methods to do our linear regression. One is using a direct formula, which is already implemented in a library, which we didn't do from scratch. And one is using a concept known as gradient descent, which is very important, which uses the concepts of gradients to minimize a particular function, which in our case was the loss function that we defined, which was nothing but the difference between the actual data point and what was predicted by the linear model, right? So that was a linear regression. And linear regression in machine learning lingo is nothing but, fitting a particular line through your data, right? So that it gives a good indicator of the relation between your x's and your y's, right? Which is x is your inputs and y is your outputs. In our case, x was the date, y was the price of the model. So you want to find the relation between them, and that's basically linear regression. Let's actually now, okay. Linear regression in machine learning lingo is all about predicting a particular value given certain x. So whenever you give an x, you expect the value to be a real number, right? So for example, when you given a date, you want it to be a number a continuous number that indicates the price of the stock, right? So it can range anywhere from minus infinity to plus infinity, ideally aligned, right? I wanted to point out something that someone pointed out last time, which was why the bias of this model was not improving beyond what was initialized bias. So for example, we initialized it at 0 and the bias remained at 0, even though the weight, which is the slope of the line, changed. Why didn't that change? And so after some thinking, and I don't remember the name of the person, but that person actually also gave his inputs into this. Thank you for that. So here's the problem that we're trying to solve. Here is the problem that we were facing actually. So if you guys remember, we initialized our weights and our biases as zeros, right? And where exactly? Yep. Where is it? 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 Yeah, params is equal to torch tensor 0, 0. So we initialize them as 0. And now when you go into, when you try to train an iteration using, let's say, for example, a very low learning rate, here's what happens, which is that the gradients are sort of multiplied by the, what do you call, the learning rate, which is over here 1 in x4. But the problem was that the gradients of the weights and the bias was on two very different scales, right? Because x itself is something of the order of 2500. So you're talking about values from 0 to 2500. right? That is what we analyzed from our X. So our days, right, went from 0 to 2500, right? And so because of this huge value of X, we had to like reduce the learning rate to something like 1 in X7, right? Which is 10 to the power minus 7, which is fine. But 1 in X7 multiplied by the gradient of W, which is X itself, comes something on the order of 1 in X3 or 1 in X4, right? But the gradient of bias, which is nothing but the learning rate itself, is nothing but like of the order of 1 in X7. So while our weight was still increasing because the amount by which we're changing in one iteration is quite high, the bias was not, because the amount by which we were changing was very, very small in comparison to the other, right? So which is why I couldn't change at all. So our goal usually is to bring the gradients of all the components on the same scale, which is why we introduce a concept which is known as normalization. All right. So here is a model Wx plus B. Our goal is to bring the gradients of W and B on the same scale, for which we have to do some changes to this X, So now here is something. Now, because B, the amount by which we're going to be changing B is going to be 1 in X7, we also want ideally that W should be around the same value. So the best way to do that is to ensure that X would be somewhere between 0 and 1, or 0 and 10, or something like that. But it shouldn't be as far as, like X is on the scale of 1000 and B. So the order of magnitude difference becomes like of the factor of 1000. That shouldn't be the case. But anywhere from 0 to 1 or 0 to 10 is fine. So right now our values are something like 2500. I would ideally want it to be between, so I would probably divide it by 100 or by 1000, so that it becomes 0 to 2.5. That's still a manageable range, so to say. So let's see, where have I taken my X's and my Y's. Right. Yep. So here is our initial X's, which is 0 to 2500. I would probably divide my X's by 1000, and to divide a tensor in PyTorch is given by this divide underscore. Now, whenever you see an underscore, remember that underscore is nothing but replacing on the spot. So for example, it doesn't necessarily allocate a new tensor outside of whatever tensor you're doing the operation on. And an underscore basically does an in-place operation, in the sense that the same tensor values, I mean, without allocating a new memory, the values in the same tensor are replaced with whatever you want to do. So divide underscore basically means that each element is divided by 1000 on spot itself without making a separate copy of it, which is how usually normal operations work. Like if, for example, I remove this underscore, it will probably allocate a new tensor and will return that to me, which is something that I don't care about. Like, I don't want to waste my memory. Anyways, make sure that you never normalize your outputs. Your model is perfectly capable of scaling to whatever, range your Y's are on. The biggest, the elephant in the room that we're trying to address is to bring the gradients on the same scale and not the values itself. And which is why inputs have to be normalized, because the gradients of weights are dependent on the inputs themselves. Once you do that, you would probably see that now your model is starting to learn pretty well. Like, for example, I initialized at 0, 0, but where have I trained it? Train one iteration. Yep, over here. Yep. Now you would see that your bias is getting learned as well. All right, so that was that. And then we also looked at deployment, which is fine. Now let's look at another concept which is called as logistic regression. Now, when you now don't be very confused by what this lingo basically means, but logistic regression is a sort of a misnomer in the sense it's not really a regression problem. We're trying to classify two different values. So either a cat or a dog, yes or a no. So that's called classification, right? So it's actually a classification model. You'll see why it's called a regression model. It's not actually very different from a linear regression model itself. And basically the same concepts follow, except one very small change, which we're going to look at. So it's classification, not really regression. And so logistic regression, whenever you look at logistic regression, think of classification. That's all I'm trying to say. All right. We'll start by picking up a problem and then we'll slowly start to build it. So there's a very famous problem on Kaggle, which is called the Titanic problem, all right? Which Titanic Kaggle, which is basically predicting who, like, there's data basically given for each passenger, and we have to determine which passenger survives and which passenger dies. So it's basically a classification problem. Either a person survives or the person does not survive. Yes or no, right? So I'm pasting the link in the notebook as well as on the chat. The Titanic problem. The link which is given over here, I'm pasting it on the chat as well. All right. And if you look over here, you'll find, and you go to the data tab, you'll probably see this data about this passenger ID. And there's information given about whether the passenger survived or not. And now there is probably information. Okay, so there are 25 columns. And how do you take a look at them? Just give a second. Yep, so there's information given like this. Sorry about the noise, guys. I'll probably wear my headphones. Can you guys hear me? Hello. Yeah. All right. So if you go to the Titanic dataset, you'll probably find information about the person's gender, the person's age, number of siblings or spouses aboard the Titanic, which might or might not affect your what do you call the chances of survival, but maybe yes. We'll take a look at that. Parts, which is number of parents or children aboard the Titanic. Ticket number, which probably determines like which coach you belong to. Fare, I mean, the lower the fare, it probably means that you're from a lower category and you probably have a higher chance of dying than to live. Cabin also determines like if so Titanic basically sank backwards, so the cabins on the back would probably obviously die, and because they wouldn't have got a chance to escape. The people at the front still do have certain chance of escaping, and port of embarkation probably also dependent, probably also determines whether the chance of survival, because there are certain rich towns and there are certain poor towns. Anyways, we'll start by downloading this data set. So I'm gonna copy the same 2 lines of code that we used to upload our files, or 3 lines of code. That right? And I hope you guys still have your kaggle.json file saved on your folders if you on your systems.
If you don't, probably you should go and download it again very fast. So I probably do have my file kaggle.json, so I'm going to upload that. And then I'm going to move that kaggle.json file, which the code is again at the top. I've probably copied it from there. And I'm going to shift it to a directory on this Linux system where Google Colab is expecting to find kaggle.json. All right. I'm gonna make this. I'm gonna make a directory over here named as Titanic itself, so that it becomes easier for me to organize my data. I'm gonna change my location to that directory itself, which is given by CD in Linux. Now this percentage sign is actually very similar to this exclamation mark, which also tells Google Colab that we're working on Linux and not Python. But percent basically is sort of a permanent change. So I want to permanently change my location to the Titanic folder and not temporarily for this session at least. So that's for that. But don't worry about that. Just follow me. And if you go over here and look at the API for downloading the data, you'll probably, yeah, Google Competitions download C Titanic. So I'm just going to go over here. I'm just going to paste it over here, right? And let's see. Yep. And it's downloading the data. Let's probably look at what data we have right now. And there are three folders over here, three files over here: train.csv, test.csv, and gendersubmission.csv. Now, here's a very important concept in machine learning in general. I'm assuming most of you guys know, but for anyone who does not know, whenever we are dealing with a machine learning problem or a deep learning problem, we always divide the data into a training data set and a validation data set, or a testing data set. A validation data set and a testing data set are basically one and the same thing. And what the training data set is, training data set is basically the data that your model gets to be trained on. And the testing data set is something that your model does not get to have a look at all anywhere in the training process, but it only gets to have a look at it once you have trained your model, so that you can check how good your model is performing. Now, why not simply, like analyze the performance of your model based on the results of your training data set itself? Now, that's because when you're training your model on the training data set, you're sort of cheating, right? Your model is learning to perform well on the training data set regardless, right? So, I mean, there is a certain bias that you've induced within your model towards your training data set. And so you cannot get a good idea about how good your model will work in the actual world or on new data through the training data set itself. Because of which you actually want a separate data set, which your model does not get to see during the training process, so that you actually can understand how your model will actually work on real data that your model has never seen, which is actually a true test of its performance, right? Sometimes they'll actually give you training and testing data sets separately, but I mean, many a times you'll see that they're basically one and the same. So we'll have to manually first split the data randomly into training and testing data set. A good ratio is about probably like 80% into the training data set and 20% into validation data set, right? But okay, that's all for another session. And when we're sort of training a model, we're only going to be using the train.csv file. A CSV file is nothing but an Excel-like file. And if you guys remember from last time, we sort of, we analyzed our CSV file using a library known as pandas. So I'm going to import my pandas as PD. And I'm going to create a data frame, which is equal to pd.readcsv. And the name of the file, which is train.csv. And let's look at certain, the head of the data set, which is nothing but the first 5 rows of this data set. All right, so you see, so there's a passenger ID that goes on from 1, 2, 3, 4, 5, so on and so forth. This is a target variable, 0 or 1. So 0 basically means, you can probably go over here and see what each means. So 0 is equal to no, means they did not survive, and 1 basically means that they did survive. So that will be so given all this data, I want to create a classification model that would predict whether the passengers survived or did not survive. All right. So there's name. Name is probably not important to us. Probably might be if you create a model that could identify which name is a sort of a poor person's name and which name is a rich person's name. But that's way too complicated. We're not. Sex probably matters because for anyone, if you've seen the movie Titanic, women and children were allowed to alight first, followed by men at the last. Age probably matters. Old people and children were let to escape first. Fare matters, and so on and so forth. So I'm going to be choosing certain variables that I think are going to be important, but here's what you should do. Okay. Okay. I'm also going to, since I'm going to be needing my testing data set, I'm going to be, taking the testing data set separately. But but you guys can do that separately. But what I want to show you is how do you actually divide your data sets into, let's say, when you don't have, let's say, a proper split between training and testing data set. So, I mean, ideally, what I can do is probably also create another data frame and work off of that. So, data frame test, for example, which is going to be nothing but my test CSV itself. You can either do that, or you can actually also what you can do is you can actually split this training data set itself into training and testing data set. I'm going to be doing that just to show you how do you actually go about that process, because it's a very important lesson. I'd say most of the times in the real world you're not going to be seeing a predefined training and testing data set. You're going to have to decide which data goes into your training data set and which data goes into your testing data set. All right, so I told you that we probably have to split a data set into an 80-20 split, which means an 80%, the 80% of the data goes into training data set itself and testing, and the remaining 20 goes into testing. So for that, I'm going to first have to determine what's actually the length of this entire data frame so that I can do an 80-20 split. And then probably going to do a train df is equal to data frame. Now to access to get a range of rows itself, you use a attribute known as ilog, which is, and then I'm going to be taking my data till whatever number is 80% of this given length. Now, length times 0.8 can be a fraction too, like a decimal point. So, which is why I have to first convert it into an integer, right? Because you can't index fractions. You can only index whole numbers. And then the remaining testing data sets is, of course, the remaining part of it, which is from the point from which marks 80% till the end of the data set itself. So now let's take a look at what's actually the length of the data frames that we've created over here. All right, so you have 712 rows in the training data set and 179 rows in the testing data set, which is good. It's a nice testing. It's a nice train test split. Works for us. Now we're going to be looking at another very important concept, which is known as pre-processing of data. It's nothing but changes that you have to do to your data so that machine learning models or computer models in general can understand them. Now, what do I mean by that? Look at certain features over here. You have sex, which is defined as male and female. Now, computers don't understand male and female. Computers only understand numbers, right? So we have to first process this data in a form that can be understood by the computer itself, which is the entire point of pre-processing. Pre-processing is nothing but converting your data into a format that your machine learning or your computer models can understand. Now, computers cannot understand male and female. Computers can only understand ones and zeros. So I'm probably going to be changing a data set I mean, I'm going to change my males to ones and females to zeros, or vice versa, doesn't matter. So for that, I'm just going to be writing one line of code. So column is sex. It's going to be nothing but 1 if I is true, else 0 for I in plain df sex is equal to male. So this over here is going to be returning a sort of lists of trues and false. So wherever there is male, it's going to be returning a true, and otherwise it's going to return a false. And if it's true, it's going to replace it with a 1. Otherwise, it's going to replace it with a 0. All right. And similarly, I need to do that for a testing data set as well. Is equal to, I'm just going to be copying this. And I'm going to be changing this to the test df. All right, let's look at one of these for once. And yes, sex has now been changed to zeros and ones. All right. What else? Now look at this. There are certain values over here like nans. Now nan is a very Python specific thing. Nan basically stands for not a number, which basically means that it's a void value, means there is no information about that passenger's cabin information, for example. So any empty data, any empty memory location is denoted by not a number or a nan. Now computers again cannot understand that. So I think the best way to do that is probably drop all of the rows in which there are any empty values over here. Pandas actually gives me a way to do that. So the way you do that is, now there are many ways to handle these not a number values. One way is to simply replace them by default value. So I could probably replace them with some default value, or you can simply like drop all of those rows in which there are any missing values, for example. Now, I think that's only feasible if like it does not totally affect the amount of data that you have. Like what if, let's say 60% of data has at least one empty value? So you can't lose 60% of your data. Like that's just crazy. So you'll have to choose according to your situation. Anyways, and Pandas actually gives me a method to drop all of the rows in which there are any empty values, which is given by drop NA. All right. And similarly, I'm going to just do that with my testing data frame as well. All right, now, all right, df.na, all right, len ndf and len test df, just to see how much data we've actually lost. Oh, sorry, drop. All right, so turns out we've actually lost quite a lot of data. So if I was actually solving this problem, I would probably not use this method. All right. But for time being, let's just actually stick with this, and we'll actually optimize this in our second run once we have time. All right. So now, I want to choose, like, just like last time, if you remember, I had to choose one particular certain columns or certain features as my x's and one particular value as my y. right? So this process is actually known as feature selection, in which you're actually choosing what features to include within your model, all right? So this is known as feature selection. Right. I want to choose certain features which I think are absolutely like guarantee or like determine the chances of a person's survival. So I'd say sex matters, age matters. I'd say number of siblings or spouses matters because families were also let out first. All right. Similarly, number of parents, children also matters for the same reasons. Sebastian parts basically belong to the same thing. And fair, I'd say fair matters because it determines whether or not a person, I mean, to which class did he belong to. All right. So I'm going to be making a list of all those values. So sex, uh, age, SIB, SP, mixture of the which letter is capital and which is not, right? And fair, all right. And there is always just one target variable, which over here is survive, which is nothing but zeros and ones. And remember that some of these values are categorical, which means some of them are only zeros and while other values are continuous variables. And so here's usually something that we always or almost always want to do with continuous variables. Continuous variables basically means anything that is not explicitly like categorical. For example, over here, age is a continuous variable. Like for example, it can range anywhere from 0 to let's say 99 or 100. All right. Now you might argue that there are only 100 values within age, so it becomes categorical. Yes, you're technically right, but age itself is like such a large range that it's stupid to consider age as a categorical variable. Let's say, for example, categorical, you almost always deal with, let's say, maximum 4 or 5, maybe 10 categories, right? If you're dealing with simple models. And so I would rather consider age as a continuous variable, all right? I would also consider my fare as a continuous variable. It can range anywhere from 0 to, I don't know, what's the maximum value. Let's say $1,000, all right? And now here is again the problem that we were facing last time, which was normalization. And so now we want to normalize this data so that it comes on the same scale as all my other data. Why do you want to do that? So that your gradients come on the same scale. And so now you see that all these other values, let's say, for example, sex is 0 and 1. So it's on that range, right? Like anywhere from 0 to 10, your categories. If you have, let's say, if you have 3 categories, it will be 0, 1, 2. So you want to bring that somewhere around that category itself. You'll probably have to normalize your age, and you're going to have to normalize your fare as well. So I'm going to be making a list of those values which I want to normalize. Normalize list is equal to age. And then fare too. All right. All right. Now I'm going to be, I've already imported like PyTorch, but I'm going to do that again just for sake of completeness. In case you guys haven't run the part which was above this, I really should not have to do that. So I'm going to create a function that normalizes my x, all right? There's nothing but standard definition of normalization as in mathematics. All you do is that so if you remember the definition of normalization, it was something like something minus its mean divided by the standard deviation. I'm just going to be doing the same. So x is equal to torch.tensor because I'll probably have lists at first, all right? And I'm just going to be simply returning x minus x dot mean, which is the average, and divided by the standard deviation. And PyTorch actually gives us functions to do that. All right. I'm going to be defining a function that takes in all my data frame, and it returns me the final x and my y. All right. So I'm going to have a get tensors from data frame. It takes in the data frame as an input, takes in whatever features I have, which is all these 5 values over here. It takes in the target, it takes in the normalized list as well, which tells me like which values I want to normalize and which I don't want to. I'm writing this function. Now, why am I writing functions and not directly doing operations on my data frame itself? It's because I want to keep it sort of flexible. Let's say tomorrow you decide that you don't want a certain feature, or tomorrow you decide that you want to include another feature. And so you have the option to completely customize this and not have to do changes within your code every time. So this code, I'm going to be writing this definition, which is going to be taking care of it for all certain possible values. All right, I'm going to be creating an X, which is initially going to be a list. Now I'm creating a list because it's easier to append values to a list. And then finally, at the end, I can probably convert it into a PyTorch tensor at once. I'm going to be iterating through each of the features within this feature list that I have. Feature list, features. Feature value is equal to list df feature. All right, so I'm going to be tapping into a certain column and I'm going to be converting all the values to a list. I'm dealing with lists because it's probably easier to handle values in list. Now, if feature in normalized list, I'm going to have to change the value feature. I'm going to have to change the values of the feature and in a normalized way. I'm going to be passing all the values of that column to my normalized function, which is going to return me the normalized values. Normalize feature values. All right. Now, finally, what I'm going to do is that x.append torch.tensor feature values. So x is going to be a list of all the tensors of all the column feature values that I'm going to be having. I mean, so each column is going to be represented by one particular tensor, and then I'm going to be concatenating all of them into one particular big tensor. All right, that works. So x is now x is now a list of all features in TensorFlow. All right. But again, now what we're going to do is that now I'm going to be concatenating all these tensors into one big tensor, right? So that so that my PyTorch models can actually handle them. My PyTorch models always expect tensors and not lists. And so, by the way, a tensor is not necessarily only one dimensional. It can be 2-dimensional, 3-dimensional, and so on and so forth. Just like you can have lists and then lists of lists and then lists of lists of lists. Just like in C++, you must have read about concepts like arrays and then 2D arrays and then 3D arrays. Very similar to that, you have tensors which can go into 2D, 3D, and so on and so forth. So over here, we're looking at 2D arrays in which one of the array would represent probably, let's say, columns and one would represent rows. My y is going to be nothing but torch.tensor df target.values, which is values again returns lists. And then I'm going to be returning torch.stack x. Now, why am I doing torch.stack? So that it actually puts them up on. So it's going to take a row. It's going to put another row on top of. So it's going to take a tensor, put another tensor on top of it, another tensor on top of it. So it becomes a 2D tensor, so to say, right? And then I'm going to have to change the order. Okay, let me actually take a look at. Let me actually. I'll do some changes to this later on. But all right. Let's actually see what kind of data we have over here. So I'm going to be having my training and my testing data sets separately. And each of them is going to have a separate X and a separate Y. So I'm going to be using this function. And over here, I'm just going to do a train df. All right. My x test and my y test also going to be the same function, except it's going to be test here. Right. Let's look at x test dot shape, x train dot shape, y train dot shape, just to get an idea. All right. So there's an error over here, which is that so okay, I've probably made a mistake in. All right, I get it over here. Now, I'm defining feature value, so I'm going to be making this feature values. So there's so the shape of my let's say y is nothing but 147, which is 147 zeros and ones, right? And then my output, sorry, my input is a 2D sort of tensor in which the first dimension is 5, which is number of features that we have, and the second say dimension is 147. Now, this is actually a problem because you almost always pass in your data in the forms of like rows comma columns. Like the dimensions are always, the first dimension is always rows, second dimension is always columns. And PyTorch also treats your data expecting that you've done that, because it sort of expects that the features, if you want to tap into let's say one particular row, you would sort of tap into the first dimension and not in the second dimension, right? PyTorch expects that. So when you want to go to one particular row out of these 147 rows, you would actually have to tap into this. So I would actually have to swap these two axes. And to do that is actually a function known as dot permute. And you can write in whatever order you want your data to be in. So by default, your order of axis is going to be axis 0, axis 1, axis 2, axis 3, and so on and so forth. Over here, we just have 0 and 1. You can change it to 1, 0, and it will actually automatically like swap those axes in that particular order. Now, we're going to be looking at other. So if you have, let's say, 10, you can actually decide what order you want it in. So you can have something like 0, 3, 5, 7, 2, 10, whatever. And so you can determine which order you want your axis to be swapped in, right? Now let's look at the shape. Yep, now it's fine. The first dimension is the number of rows and the second dimension is the columns. All right. That's that. So we now have our data itself, and we have our x's and y's. Now, your x and your y collectively forms your data set. And so I want to create sort of a, so I don't want to handle them separately. I want to probably combine them into one particular list. So I'm probably going to be creating a list of tuples in which the tuple is going to contain x's and y's. So here's what I'm going to do. And that is what I'm going to be calling my data set. All right. So my data set is nothing but a list of my x's and my y combined, right? And my test data set is also going to be something like that. Zip x test, y test. Let's look at what train data set looks like. Yep. So it's a list of tuples in which the first part of the tuple is going to be my x and the second tensor, and the second is going to be my y, right? Another x, another y, another x, another y, and so on and so forth. Now notice that PyTorch has already converted your integers into floats or decimal values. That's because your machine learning models also don't understand continuous variables, categorical variables. They explicitly can only handle floats, and that is how PyTorch works. That's a thing, because you're always going to be doing float operations onto them. When you multiply it with, let's say, w itself is going to be a float, and so a float by float operation is much more easier than a float by integer operation, because PyTorch otherwise internally would have to first convert an integer into a float, which takes in certain extra time. So that's also a sort of a pre-processing that goes on, behind the scenes. I'm going to be, so here's a very, very important concept from a very practical point of view and not theoretical at all, which is something known as a data loader. What a data loader is basically something that can, okay. I'll teach you guys about a concept known as batches. Now, you have two ways to, let's say, put your data through your model. One is that you individually feed each of these rows and each of these columns, like you feed this row and then you expect your model to, do the gradient descent on that and learn from this, and then you feed it the other row and so on and so forth. You can do that. Or you can actually, like my entire tensor, which is 147,5, 147, I can also feed that into my GPU all at once. And my PyTorch is actually optimized in such a way that it can handle all of these values all at once. So it's gonna multiply my entire this tensor with my weights and add it with the bias, and then it's gonna calculate the gradients and so on and so forth. Most of the times when you're dealing with big data, which is all the rage nowadays, you have, let's say, millions or 50 million data points at once, and you cannot feed all of them together. But feeding them one by one is also very slow. So we divide them into small chunks known as batches. So which probably means that I'm probably going to be feeding, let's say, 16 or 32 rows at once. That's still manageable. So 50 million at once is not manageable. One is not feasible. So let's say something in between, let's say 16 rows at once is probably doable. I can ideally like divide these tensors, like I can write a piece of function which divides them into these chunks, which is very cumbersome. So I'm going to be using a data structure from PyTorch, which actually does this for me. And this data structure is known as a data loader, which is nothing but a function which takes in your data and it expects your data to be in the form of tuples of x's and y's. And it divides your data into batches, and it also has some additional functionality which can automatically feed your data into the GPU without actually too much hassle. Like otherwise your data by default is on CPU, and to shift it on GPU you actually have to do some additional sort of coding and so forth, which we'll look at later. In this lab session, we're not using our CPU, our GPU at all. We're only using our CPUs. But anyways, to use actually the data loader, you actually have to go to torch.utils.data and import data loader with a capital D and a capital L. Make sure of that. And my train DL is going to be data loader. It's going to take in the data set, which is nothing but a list, an iterable of tuples of x's and y's, in which the tuple is x comma y, and it takes an additional input, which is batch size. Over here I'm just going to say that it's 16. Test DL is also going to be the same. Test D set, batch size is equal to 60 for now. Right, it works. Here's a very cool thing about Google Colab. Now, whenever you want to see the definition of a particular function, all right, all you have to do in Google Colab is type question mark, and the name of the function itself, or the name of the class itself. So when I do this, it's going to give me the definition of the class itself. So let's look at this. So over here, you see that it has given me something that here's a class which takes in certain arguments and certain keywords. Let's look at what all it can take. So here's the initialization function. It takes in the data set and it takes in the batch size. Now batch size is optional. If you don't, let's say, specify it, it's going to be defaulted to 1. And the data set in PyTorch is expected to be, let's say, tuples of x's and y's. And if you want to look at, there are also other options like shuffle, which means that you can shuffle your data set, like to ensure that the data set is not in the same order as that. But anyways, this is that. TrainDL is now actually sort of an iterable, which means that you can sort of iterate through TrainDL and get x's and y's very fast. All right, and I'll show you how you do that. Before I do that, but I'm actually, last time, if you remember in linear regression, I sort of, I don't like this function at all because it's, okay, let me actually copy this over here. So this is my training definition that I created. It takes step one, it calculates, you first have to define a model, which over here is nothing but, what do you call, if your W times X plus B, you calculate the loss, you calculate the gradients, and then you do the gradient descent equation. The problem with this is that it's too much hard coded, and I don't probably like it, and I would probably like to introduce some sort of flexibility. One very good way to do is to actually define functions, not rather than like do the calculations over here itself, but rather define functions which you can actually change on the go, and you can change that function and not have to change this entire function from scratch to do some sort of other task, right? For example, so I'm not going to be using this. I'm going to be defining, let's say, other. I'm going to be defining functions that I can modify later on. I'm going to be defining a function that takes in your x and your y, it calculates it, and it calculates the gradients and gives it back to you. So it's going to take my x, it's going to take my y, it's also going to take my model. So first of all, pred is equal to model x. This is basically this part, by the way. This is the part that I'm trying to do. Model x, loss is equal to loss fn pred comma y. And loss dot backward. So this is what I'm expecting this model to do. All right. I'm going to be defining one function, which is this entire training process over here. Now, this iteration over here is also known as epoch in machine learning lingo, very important. So I'm going to be naming this function train epoch. And it's going to take the model, it's going to take in learning rate. It's also going to take the list of parameters that we have. All right. And now look at how I'm going to be using my data loaders over here. So for x comma y in TrainDL, that's all you have to do. Okay, by the way, if you wanna, if you're doubting like how this works, let's actually also look at how data loaders actually work as iterables. So for x comma y in TrainDL, print x dot shape comma y dot shape. All right. Look at this. So x comma y is now acting like, so TrainDL is now an iterable, which you can iterate through using a for loop. All right. And there are, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 different let's say chunks that this data loader has divided data into. Because there were about 179 rows, makes sense. All right. Now notice that the very last chunk over here does not have 16 data points, which makes sense because we had only 179 data points. So if you 160 times 11 is 176, and then 177, 8, and 179 would have to be put into a separate batch. We're actually going to have to deal this separately later on, but anyways, that's about that. So for each of these, what I'm going to do is that I'm going to be passing my data through the gradient, through the process which takes in my x's, takes in my y, and the model, and it calculates the gradients. Now for p in params, p dot data minus is equal to LR times p dot grad. And then finally, you're also going to have to do a p.grad dot zero underscore. Now, again, why underscore? It's because I don't want to probably allocate a memory separately because it's a break in the computational graph. So you do an in-place replacement of that value with zeros. I want to check how my model is actually going to work. So I'm going to be defining something known as a metric. Now, what are metrics? Metrics are nothing but functions which determine how good your model is working. Over here, I think an accuracy is a good model, which means basically tells like out of all the times that you predicted zeros and ones, how many times were you actually right? So let's say out of 100 times, I was correctly able to identify uh, uh, like which of them survived and which of them did not survive. I was probably able to do that 95% of the times. So my accuracy probably should return me a value of 0.95 given my predictions and the actual wise. Now, why didn't we define this accuracy in the previous linear regression problem? It's because you can't actually define, there is actually no right or wrong per se, right? There is only how close you actually came to your actual value, which is why we actually predict, we printed our loss values. Loss was a good indicator of how good your model is performing. The lower the loss, the better your model is. Now over here, I mean, because there is no right and wrong, your model can only, like, you're only predicting a real value of the price of the stock, right? So I think a good measure to do that, the only way to measure is how close you were actually able to predict to the actual price of the model in real world. Over here, there is nothing known as close. It's either right or wrong. You either survived or you did not survive. So good metric to do that is accuracy. Accuracy is a metric. So was loss function in a previous value, but I mean, technically, loss and accuracy are two very different concepts and should be kept separate. We'll talk about that separately. So here's how I'm defining my threads. Now, your neural network model does not output zeros and ones. It can only output values, a continuous value, because that's how, I mean, you're doing W times X plus B, right? That itself is a continuous variable. And so you're going to have to do some certain processing. What I'm going to do is, let me actually first define my model. Yep. Because I think that's quite important. So def logistic regression model, right? And it's going to take an X. What it's going to return is going to return the same thing, X times weights plus bias. Now, where this is not X star. I mean, in Python, usually you do an X star. But that X comma star in a previous case was basically X was just one variable and W was just another variable. Now you can, now X over here is not necessarily just one value. It's a tensor containing 5 different values. And when you do a star, PyTorch actually does an in-place multiplication. So okay. I'll give you an example. Let's say one of my tensors is 1, 2, 3, 4, 5, multiplied by, let's say, my W, which is also 1, 2, 3, 4, 5. All right. When you do a star, Python actually assumes that you're doing a dot operation, which means that 1 will be multiplied by this one, 2 will be multiplied by this 2, 3 will be multiplied by this 3, 4 will be multiplied by 4, and 5 will be multiplied by 5. So that will give me what? 1 plus 4 plus 9 plus 16 plus 25, whatever the value is. The problem is that the way we actually want to do these operations is do a tensor multiplication, which or a array multiplication, or a, if you guys remember that, you know, you first have to do a transpose, and then so what you're actually trying to do is x multiplied by w transpose or w dash or whatever that. That's an entirely mathematical concept, right? You guys learn about this in theory classes, but if not, I mean, the reason why you're actually trying to do that is because x is, let's say, a tensor of 5, sorry, 140, or let's say one row is, I'm just considering one row over here. So it's a tensor of shape 1, comma 5. My w is also a tensor of 1, comma 5. When you actually do a in place like a dot operation, you're again gonna get a tensor of 1, comma 5. All right. I actually just want one particular value, which is nothing but x1 x1 w1 plus x2 w2 plus x3 w. This is going to be one particular value. I want a one particular value. I don't want this tensor, and so for that, I'm going to have to do x multiplied by w transpose, which is going to be 1, comma 5 multiplied by 5, comma 1. I mean, a tensor of shape 1, comma 5 multiplied by tensor of 5, comma 1. And if you remember tensor operations, this inner loop, reduces, and you basically will get the tensor of 1, comma 1. That is exactly the logic that I'm trying to go over here. Now, which is why this star won't work now, because this sort of array multiplication or this sort of tensor multiplication operation was actually so famous. Yeah, I can actually either do this. Sorry. Okay. So it was actually so. Sorry. Let me go back. This star won't work because it's simply going to return me a tensor of 5 values, and I don't want that. I basically want sort of like an array multiplication of 2 values, which is going to return me one particular value. That is actually given by this Python operator, which is known as at the rate of. Very important. All right. That's that. That is your normal linear regression model, if you guys remember. All right. Now, because I want my value, so here's what I'm thinking of doing. All right. And let me let me actually explain to you how mathematicians actually came up with a clever way to convert this existing linear regression model into a classification model. Am I not presenting my screen? Oh, I closed my screen. Just give me a second. Or closed it by mistake. Oh, no, not over here. Just give me a second. All right. Yep. Sorry about that, guys. Now, because I'm trying to get values between 0 and 1, I first have to reduce. Now, my output of this particular model over here. Do I have to run this entire thing again? When I run this thing and close this thing. I'm going to run this again just for completeness sake. All right. This value, this value over here that it's gonna be one particular continuous value, all right? And this value can range from minus infinity to plus infinity. I want my values between 0 and 1. So I think the very first step that I want to do is actually compress all those values, scale all those values from minus infinity to plus, from 0 to 1. Now there's a very convenient function in mathematics which is known as the sigmoid function, all right, which is basically this is the all right. Let me actually show you what the sigmoid function looks like. Oh, but I'm not presenting my screen. Can you guys see my screen?
Yeah, we can.
Sorry guys for that small issue over there. But sorry, this was what I was saying. So x times weight plus bias is going to be one continuous variable value. It's going to range from minus infinity to plus infinity, but I want to compress it between 0 and 1, first of all, because my values are my survived and not survived is actually between 0 and 1. All right. So there's a very convenient function in mathematics which is known as the sigmoid function, which takes in values from minus infinity to plus infinity, and it always compresses them between 0 and 1. All right. And any value which is greater than 0, for example, ranges from 0.5 to 1. It sort of like tapers off. It sort of has an asymptote at plus 1, and on the lower end, it also has an asymptote at 0, which is achieved at negative infinity. And at plus infinity, there's it asymptotes at plus 1. So that's exactly what we want. So I'm going to pass these inputs, whatever this value is, through this function, which is torch.sigmoid. I'm going to tell you the definition of torch.sigmoid. Torch.sigmoid is actually defined as fx is equal to 1 divided by 1 plus e to the power of negative x. This is basically the definition of this function over here. All right. All right. And this value, I know for sure is going to be ranging from 0 to 1. Now, here's the problem that I have. This again is a continuous function, and I want a categorical value between either a 0 or a 1, has survived or not survived. All right. Here's what I'm going to do. Any value which is greater than 0.5, I'm going to assume that my model is sure. So my model is predicting that the person has survived rather than not survived. You can consider this as a probability. So if there is a 0.6% probability of a person surviving, probably you can assume that the model, what would you rather choose, that the person has survived or not survived? If the probability is 0.6, you would probably say that the person has survived because it's much more closer to 1 than to 0. All right. So I'm going to create a threshold at 0.5. All right. So any values from 0.5 to 1, I'm going to say that the person has survived. Any values from 0.5 to 1, I'm going to say the person has not survived. All right. So that is my linear logistic regression model. All right. And now what I'm going to do is that in my accuracy function, I'm going to say that for any value which is greater than, let's say, 0.5, right? And I'm going to compare it to my actual ground truth value, which are obviously zeros and ones. That's going to be a list of what do you call trues and false. So wherever the person has actually not survived, and my model is also predicting that the person has not survived, in which the prediction will be between 0 and 0.5. I'm going to say that the model is right, and my accuracy is going to increase, and otherwise it's going to decrease. So I'm going to get a list of trues and false, and now I want to check what percentage of this actual list of trues and false is true, and that's basically going to be my accuracy. So out of 20 times, if my model predicts 19 times that this list has 19 trues and 1 false, it basically means that my model is 95% accurate. All right. Trues and false first have to be converted into zeros and ones. But computers don't understand trues and false, so that's done by this float function, and I'm going to take the mean of that, which is going to tell me that. Now I'm going to have to write a separate function for what do you call my validation stuff as well, because training. You've trained the model, but now you actually want to check how your model is performing in the training or the validation data set or the testing data set, one and the same thing. I'm going to create a variable known as accuracy underscore because I've already used this keyword accuracy and I don't want to use that again. Sorry. Yep. What I'm going to do is that I'm going to create a list. All right. Now, again, I'm going to have to iterate through all these X's and Y's in this testing data loader, and I'm going to have to sort of calculate the accuracy separately. And then what I'm going to do is that I'm going to have to take the mean of all those accuracies and return that value. Anyways, accuracy model X, comma Y, model X because that's going to give me the predicted value. Okay. For X, comma Y in test DL, all right? And now what I'm going to do is I'm going to return torch.stack accuracy because I have a list and the dot mean only works on tensor, so you first have to convert that list into a tensor. So again, I'm going to be using my torch.stack function. Float. All right. Yeah, that is my functions. All right. I'm going to be writing a function to initialize my parameters so that I don't have to do that again and again. All right, it's going to take in what size of parameters you want. So in my previous iteration, I only wanted 2 numbers because there was only one W and one B. Over here, the W itself is like 5 different values because there are 5 different input features. So corresponding to each one of them, you're going to have what is going to be my model, by the way. Let me just write it down. So Y over here is going to be W1 X1 plus W2 X2 plus W3 X3 plus W4 X4 plus W5 X5 plus a constant B. So so my W itself is going to have 5 different W's. It's going to be a tensor of 5 different values: W1, W2, W3, W4, W5, and then the B itself. I'm going to be returning torch.random values. I think that's a better way to initialize, as you'll see later on in deep learning stuff. And of course, it requires grad, just like we did last time. Underscore because you want to do an in place operation. Anyways, I'm going to be initializing my weights and my biases separately. Init params 5 because there are 5 values, and bias is going to be init params and just 1 value. All right. But I'm going to be, like tying them up all together in one particular what do you call tuple. And now let's take a look at what params are. Sorry, weight. Okay, I think weights is a better value better name. All right, so there's so it's a tuple of, let's say, 2 tensors. One tensor is of 5 values, which is my W, and there is one of my bias over here. All right. Now, all right, so that's about that. Now, we've basically covered like most of this stuff, but there's this one last component that we still have to consider, which is just like in the last time we were actually minimizing like the mean square error, which is actually the difference between which is a difference between let's say the predicted value and the actual ground truth value that we have. What's going to be the loss function over here? What are we exactly trying to minimize, right? And for that, for classification, because now you can't actually use the same formula over there, because over there we were actually talking about how close your predicted values to the actual value. Over here, it's right or wrong, right? It's either right or wrong. So how do you define that into a continuous function that can be minimized using gradient descent? So for that, there's actually a specific. So here's what I'm going to do. I'm going to be defining a function which is called binary classification loss. It's going to take in, let's say, the predicted the predicted values from the model and the target itself. Very first thing is, of course, asserting that these two things are of the same length, because if they're not, you're basically doing something wrong. It's a good debugging practice, all right? Right. And here's what I'm actually going to do now. Right, I'm going to write over here that I'm actually dealing with a loss function. Right. Now there is, what I'm going to do is that, okay, I want to basically give a higher penalty to the model wherever the model has gone wrong, all right? And I want to give a sort of a lower penalty to the model wherever the model has gone right. Now, you must keep in mind that the target variables is going to be categorical variables of 0 or 1. My y predictor is going to be a continuous value between 0 and 1. All right. Now my model actually predicts something as right if the y predicted value is from 0.5 to 1. So whenever my target is actually 1, my ground truth value is 1, I want to give a lower penalty to the model. So a good way to, let's say, assign a lower penalty to a model when the y predicted is between 0.5 to 1 is doing 1 minus predicted value itself. So I'm going to write the logic over here. Whenever target is 1, loss is going to be 1 minus y pred. Why? Because it's going to assign a lower penalty to, let's say, a correct prediction and a higher penalty to a lower prediction. So whenever I'm predicting wrong, whenever my target is 1 and I'm predicting a wrong prediction, which is y predicted from 0 to 0.5, it's going to be a higher penalty because I'm doing 1 minus a lower value. So it's going to be a higher penalty, all right? And whenever I'm doing right, which is 0.5 to 1, it's going to be a lower penalty. And other way around, whenever target is 0, I'm just going to simply reverse it. But anyways, and whenever target is 0, it's simply going to get reversed. Loss is simply going to be y pred, because it's going to be a higher penalty for a prediction of 1 and a lower penalty for a prediction of 0. So this is actually very conveniently, I don't have to write an if-else condition. I'm actually going to be using a function defined by PyTorch, which already does this for me, which is basically torch.where, wherever target is equal to 1, to a 1 minus y pred, wherever target is 1 and wherever target is, wherever. So let's actually look at like let's actually look at this definition of torch.where, like if you guys are confused. I know this, but I'm actually trying to show you like what exactly is the procedure of, what? There is some problem with my Google Colab. Um, all right. Oh, all right. Sorry, guys. Give me 2 more minutes. All right. So torch.where is defined as you first write a condition. So we wrote a condition over here, target is equal to 1. Whenever that condition is true, you replace the value with 1 minus ypred, and wherever the condition is false, you replace it with another value, which over here is ypred itself. So wherever target is 0, you're going to be identifying a loss value of ypred itself, and whenever the target is equal to 1, you're going to be returning 1 minus ypred. So that's basically my loss function over here. And this, of course, you have to do a mean over here because this is a tensor and you want the average of all those values. All right. Now let's take a look at this binary. Let's see what kind of values you get over here. So you have pred and then you have y batch. But let's actually take a look at, like, so for example, I'm going to be taking one particular x and one particular y, which is going to be, I'm going to be, because I already have my training and my testing data set, I'm actually going to be take the very first values from that, which is actually done using this thing known as next iter, which basically taps it into that iterable and it gets the very first iterable from that. And then thread is nothing gonna, it's nothing but I haven't initialized my model as well. Yep. So I'm gonna, so my prediction is gonna be logistic regression. What's the name of my function over here? Logistic regression model. And it's gonna take x itself, and then pred, and then y. Let's look at that. Yep. So there's I now have a loss value of 0.58 and it's a continuous value. I want to minimize this particular loss function, and now everything is basically the same. I apply the same gradient descent and how it works. All right. Let's actually run this function now. So my loss function is nothing but my binary classification loss. All right. Now what I'm going to do is that I'm going to be running it for, let's say, 100 iterations, and then I'm going to train epoch logistic regression model. I'm going to set my learning rate to, let's say, 1 in egg 1, which is 0.1, which is a very standard learning rate that you see in machine learning. Last time we didn't actually use that because of normalization. Now, when you normalize, you'll probably realize that in the last one as well, you'll probably be able to use a higher learning rate. And I'm going to be printing my validation loss. And here is where you realize why I used why I defined that validate epoch function. Validate epoch, logistic regression model. What else? All right. Test DL is not defined. Oh. There is some error and I don't know what. Let's see. Okay. Okay, let me actually put an assertion over here as well. Assert len. Oh, here is why. So I took in a key argument as pred, and then I wrote preds over here, and I must have defined pred somewhere outside, so which is why an error. But yeah, it works now. All right, and you'll see that it's working now. Accuracy is slowly increasing. So we were first at 43%, it went to 50%, 54, 56. Probably train it longer, and it'll go on until 70% as well. Maybe let's say. I doubt it'll go anywhere beyond 70%, but let's take a look. 8, 62, 64. Yeah, 64. It's actually kind of stuck at 64. All right, 62. Now it's starting to get worse because, and because of a problem which I'm not going to discuss over here, but it's something known as overshooting the minima, which you're going to be learning in the theory classes. But anyways, but you see that this model is actually working now. So so this is by the validation accuracy. I think it's not validation loss. Loss should reduce, accuracy should increase. And over here we were actually defining, learning about the accuracy. So you've now trained your what do you call this as well? What do you call? You've now defined your logistic regression model. All right, so that's about it. I'm gonna stop with this logistic regression, and now we're gonna come to lab 2. And here's what we're gonna do. All right. And let's look at let's see how much we can actually write in this particular lab session. But okay, I'm gonna want you to open up a new Google Colab notebook in your wherever you've defined your wherever you store your lab notebooks. I'm gonna be sharing this notebook, and I'm gonna sharing this over there as well with you guys, so that you can have a look at it in case you're falling behind. Do you guys have any doubts till this point? These are very important concepts, by the way, and you guys are if you guys do not know these concepts beforehand, in the sense that if you've learned anything new in this lab session, make sure that you revise it. I would recommend that you revise each one of these concepts, not only from a theoretical perspective, but also from the practical perspective during this week. Very, very important. I cannot stress this enough. I can guarantee you that if you don't do that, you're going to lose all of it, and you'll probably have to start again sometime in the future if you want to get into this. All right. Before we start, I'm gonna all right, we're going to be starting with another problem now, and we're going to and this lab session is, by the way, on building your neural networks from scratch, which, as you'll see, is nothing but an extension of your linear and your logistic regression models. Building neural networks from scratch. And you'll be surprised how similar is this to your actual logistic and your linear regression models. By the way, key takeaway from lab 1 is that the only difference in logistic regression model and your linear regression model, apart from accuracy, because accuracy is nothing but a metric, it's not part of the training process, is your loss function. That's the only change in the entire training process. Both in linear regression and logistic regression, we did have a linear model, which was nothing but y is equal to w1x1 plus w2x2. The exact same model was used. We didn't change anything. The only change was that the loss function, in which the regression problem, we were actually trying to reduce the difference between, let's say, the actual predicted value and the ground truth value. And in logistic regression, we were actually trying to reduce the error of classification, which was given by zeros or ones, basically. So basically, we were trying to maximize the accuracy or reduce the error, basically one and the same thing. You might say that there is also one more difference, which is that torch.sigmoid, but torch.sigmoid has absolutely no significance other than, like compressing the values to a certain range, right? That's exactly what we want. Now, I could ideally remove that torch.sigmoid and the model would still work fine, but the only change I would probably have to make in that sense would be to determine, like, how do you actually, like, convert the actual prediction of the model to zeros and ones, which is given by that if-else condition in that accuracy, which is that whenever y is greater than 0.5, do something, and otherwise do something else. All right, makes sense? All right, I'm going to be now, before we actually start a neural network, one thing that we always do in this lab is we first pick a problem and then we look at how do you actually go about solving that. So we actually did a classification problem, the Titanic classification problem. Now I'm going to do a sort of a more complex classification problem. What I'm going to do is that I'm going to be taking a data set which is known as the MNIST data set. Which is not a data set containing handwritten digits like these. These are images of handwritten digits. And you want your neural network to identify what handwritten digit this is. So for example, if I give this particular image at the very beginning, I want my model to predict a 5. And if the second image is given, I want my model to predict a 0. So this is a classification problem, right? Like there are only 10 digits from 0 to 9. And you're doing a classification problem in which your model has to, given an image, input image, your model has to identify what digit this is, right, from 0 to 9.
Yeah, I have a doubt from the previous notebook.
Sure.
So suppose you have something like a ticket number, like a ticket code or something, which is not a number. So it's a string of letters and numbers, something like that.
Right.
So how do you include that in your model? Because
yeah, all right. We didn't do that, but in case you want to do that, you first have to. Okay, what exactly is pre-processing? Pre-processing is nothing. So I gave you a definition, and I would slightly like to change it. Pre-processing is not only just converting it into numbers, but it's converting it into meaningful numbers, something that your model can actually use to do some prediction. So you want to first identify, like, what exactly can you derive from this ticket cabin number? Sorry, what was that feature that you were talking about?
Yeah, the ticket number. It has, say, like one class, say it'll be A123 or something like that.
A123. All right. So you want to first identify, like, what exactly you're trying to derive from that. So I would probably say that, like, I don't know this, and you probably have to look it up, like what ticket number corresponds to what category or what class. I would probably say that A category refers to the more rich people, and C refers to the poorer people, let's say, for example. All right. Or it probably might also determine, like, what deck you're on, and instead what floor you're on. And so because it might then also be possible that people on the higher floors have a higher chance of surviving than people at the bottom floor. All right. So based on that, you want to convert them into numbers. So for example, if I decide to, let's say, only process the floor number, right, which is given by ABC, it may be like, for example, A refers to the ground floor, B is second, C is third. I would probably, and then on one floor, it doesn't matter what room number you're on. So for example, if your ticket is A85, that 85 doesn't matter to me anymore. So I'm going to discard that. Do you get the idea?
Yeah, but okay. So what if we don't know that key A is like top or bottom types? So
No,
in this
then
data set also, it's not this uniform that the ticket number is like a letter joined with numbers.
no, then
It's a
then
very
you absolutely have to find out at least some relation, and that is exactly the entire problem of data science. Like getting meaningful values from it. You can't simply feed any value into your neural network or into your model and expect it to find a relation.
If you go and check the ticket, this I think data set has one
There must be
column
something,
for
right?
yeah, and I mean there is I don't know how to can't like understand how to include that in the
Right. All right. So let's do some search. All right. So Titanic ticket. Uh, uh, Titanic ship ticket. Okay. Let's go to discussions. Probably gonna write ticket. Okay. So you find, so do ticket numbers mean anything? Someone has written something, and someone might have information about it. All right. All right. There is actually an encyclopedia page on this over here. Look at this, cabin allocations. Allocations of cabins on Titanic is
okay,
a
okay.
source. Do you get it? Do you get the idea now?
Yeah, so we need to okay.
You need to do some
Okay.
search. Of course, you need to do some search. You can't. The entire point of processing your data is to get meaningful values and not just any values.
And we have
If
to
you give
convert it to
garbage,
numbers.
right? If you give garbage values to your into your mathematical model, you'll get garbage values as the output, right?
Thank you.
I'm going to be downloading this MNIST dataset over here, for which I'm going to be using a library, which is a sub-library of PyTorch itself, which is known as Torch Vision, which contains everything related to computer vision. So now I'm basically solving a sort of a computer vision problem, which is I'm dealing with images and not numbers themselves. Like I was dealing with only like data frames, which are rows and columns filled with numbers. Now I'm dealing with images, right? So that's a computer vision problem, all right? But we'll look more into computer vision into the future. For now, I'm going to be using this Torch Vision library because it contains data, everything related to computer vision, including processing, data sets. So this MNIST dataset is actually contained within this Torch Vision library. Of course, I'm going to be importing my normal PyTorch, which is import torch. And I'm also going to be importing the sum module from PyTorch known as NN, which contains every function related to neural networks. And we've already seen this NN function in the lab one. So, and if we've not, we'll probably look at it in this. So a lot of functionalities related to neural networks are given within this PyTorch. So we'll actually going to be using that. We'll see how that works. Right, so I'm going to be downloading this MNIST dataset. MNIST. Yep, this works. MNIST. All right, let's actually go to Torch Vision. You go to torchvision.datasets, and then over there you go to, let's say, there's this MNIST dataset over here, and it actually tells you how to download a dataset. It gives you like what you have to enter into this over here. So it gives you what keywords you have to enter, and you'll get some output. All right, I'm going to be using that. So over here, if you see, there is train or train. There is a argument known as train, which takes in a Boolean value of true and false. If you pass in true, it's gonna take in the training data set. Otherwise, it's gonna download the testing data set. So over here, I'm gonna keep my testing images and my training images separately. Like I'm not gonna split it from my training data set itself. It's gonna be torchvision.datasets.mnist. Root is equal to root basically means where do you want to download the data set. I'm going to be downloading in the same directory in which I'm working. Train is equal to true. Download is equal to true because I want to download my data set. And ideally, I can also apply some transformation onto that. Now, what is a transformation? Transformation is nothing but a function that is applied to each of the images within this data set itself. So by default, this data set is going to give me images, JPEG images. And what I want to do is that I will have to convert them into PyTorch tensors, because tensors is what actually matters to me a lot. Like I can only feed my machine learning model with PyTorch tensors and not JPEG images. So transform, which is nothing but any function which is applied onto that, it's going to be nothing but torchvision dot transforms dot to tensor, right? And I've, by the way, picked this up from the documentation itself. Like they had an example in which this is how they actually converted these images over here. So I've basically just copy pasted this transform function from there. Similarly, testing images, MNIST test images, train is equal to false. All right. So now let me take a look at MNIST train or MNIST test images, doesn't matter. Downloading, and my testing data set is 10,000 images, and my training data set, for example, I'd say would be 60,000 if I'm not wrong. All right, yeah. 60,000 images in the training data set and 10,000 images. So now we're already moving to a very high level complexity. We've increased the number of classes. We've increased the size of an input, which is going to be a whole image, and each image contains many, many pixels. And now we have a very large data set itself. So now obviously you can't expect like simple models to solve complex problems. You're going to have to increase the complexity of the model itself, which is where neural networks come into play. But first, let's actually visualize like what exactly this data will look like. So MNIST train images 0, it's going to contain, let's say, for example, a tuple containing your x and y, in which the very first element is going to be the tensor itself. And if you look at the shape of it, it's going to be 1, 28, 28. Now, 28 is nothing but the height. The next dimension 28 is the width, or sorry, this is width. Sorry, this is width. This is height. This over here is number of channels within the image. So images usually, like the color images that you see, contain 3 channels, which are RGB. Like you must have heard this. When you're dealing with black and white images, for example, you have only 1 channel, and each channel, and so that is basically the concept of channel. So now you're already coming into computer vision. It's a very important concept. Images that we usually deal with, color images of 3 channels, RGB, in which the values range from anywhere from 0 to 255, right? So there are 256 values in the standard RGB images that you use. Black and white images only have 10 different values from 0 to 10, which is a grayscale feature in the sense that 0 represents, let's say, white. Sorry, 0 represents black and 1 represents white, and it's a whole grayscale, 10 different values from that. And there's only one channel. There are no 3 channels over there. So that's about that. Right. If you want to take a look at let me actually show you, like, if you want to like take a look at like what this image actually looks like. PIL image. So I'm going to be using the PIL tensor to image. I'm going to be using the PIL library, which is nothing stands for Python image library. It's a very standard image processing library. And I'm actually searching how do I convert a tensor to an image. So from PIL import image, I'll do that. What else? Image is equal to open image. No, I want yep. Oh, I can use this. Okay. I don't need PIL. Okay, I need PIL. Okay, let's take a look at that. I'm going to be passing in this particular tensor over here. And because it's black and white, I need to convert it into an RGB. So let's take a look at that. Yep, there is your image over there. This is a PIL image, which is a class that handles all the JPEGs and PNG files and so on and so forth. So it's only 28 by 28 pixels, which is why it's so small. I mean, your screen is basically like what, 968 by something pixels. So this is only 28 by 20 pixels, which is why it looks very small. Anyways, I just wanted to do this to show you like how do you visualize your data. This is what your data is going to look like. I already converted it into tensors, but let's say I didn't apply this transform over here. I would have simply gotten a list of JPEGs or PNG files, or PIL files that I would have had to convert into tensors separately. Anyways, how do you visualize data? That's about that. Again, I have my data set now. Now each of my values is already a tuple of x comma y. So now I already have my data set. I don't have to do any sort of other processing. Now next step is simply to converting into data loaders. So from we have our data set. Let's now convert this into data loaders. And so I'm going to do from torch.utils.data import data loader traindl is equal to data loader list train images. Batch size is going to be, let's say, 16. Usually batch sizes are usually in the power of 2 because it's sort of like computationally efficient for the GPUs or CPUs themselves. CPUs themselves work in like powers of 2. So let's say even if you write a batch size of 15, it's going to allocate the CPU will have to allocate a memory of size 16 in powers of 2s, which is why, I mean, you're going to be basically wasting that one extra space. So it's usually always recommended to, like allocate in powers of 2s. Shuffle is equal to true. Why not? Because shuffling basically will help me ensure that my model is well generalized. This is going to be MNIST test images. Batch size is going to be 32, in fact. And shuffle is equal to false because shuffle doesn't matter actually over here. Now, why is my batch size over here twice the size of the batch size in the training data set? By the way, there is a limit that your CPU or your GPU can handle, which is why, I mean, if you remember, I told you that the model. Sorry about that. If you remember, I told you that the model cannot probably handle all of the data at once, like millions of data set, millions of data points at once. That's true. That's also true for like very large amount of batch sizes. So there's a very soft trade-off that you have to, balance, that you have to maintain. 16 is probably a good size over here, but over here, I'm going to be assigning a batch size double the size of the batch size in the training data set. The only reason is because the tensors that I'm going to be allocating over here, right? They're also going to have, so if you remember params in the last slide, params actually had a data, which is W, and then param.grad was like part of that class itself, which contained basically values of the gradients. So you're basically, for each parameter, you're actually occupying double the size of how many ever parameters you've initialized, right? But in the testing data set, we never actually use the gradients, right? We don't have to calculate gradients, which is why you can actually use double the size of batch size. So you actually have that liberty to do that. So why not? Oh no, this should be test data set, test DL. All right. Now let's look at what exactly I'm dealing with over here. So this is going to return me my x and y. So x comma y is equal to that. X dot shape, y itself. Let's take a look at this. X dot shape is going to be, there are 16 items in the batch, so 16 rows or 16 items in the batch. Each element is of shape 1, 28, 28, in which 1 is the channel, 28 is the height, and then 28 is the width over here. And then here I have 16 values which range from 0 to 9, which are nothing but actually the ground truth label of each image, what handwritten digit exactly is. So that first image would probably be 9, next image would be a 6, 4, 6, 2, 9, so on and so forth. All right. So that's my data. So I'm done with my data, and I'm actually let me. So I actually don't like writing. So I'm going to be starting to refactor my code now. I don't like writing all of this, again and again. So I'm going to be writing a sort of a function that actually that takes in my data sets and returns me the data loaders again and again. So it's gonna help me later on. So get DLs, train DS, test DS, and then batch size, which by default is going to be 1, but you have the choice to modify it. Anyways, yes, batch size is equal to BS. There's also a collate function which you have the option to use, but okay, anyways, I'm not going to be specifying that as of now. This over here is going to be batch size times 2, and this over here is going to be test DS. Right? And I'm going to be basically returning train DL and test DL. Yep. Anyways, that's done now. So now I'm done with my data. Now my next part is the model itself. So so I'm done with my data. Now I'm going to be dealing with the model. And here is what I'm going to do is I'm going to be introducing the concept of neural networks, and then we'll probably stop, and then we'll probably continue this in the next lab session. But let me talk to you about the concept of neural networks. What exactly are neural networks? And there is actually a very particular class of neural networks, which is the most fundamental and the most basic type of neural network, which is known as a multi-layer perceptron. So if you remember, if you remember, my linear model was nothing but W times X plus B. Right? Now, W times x and W themselves can be tensors. So this Wx can actually be W1x1 plus W2x2, or in general, just W at x plus b. All right. Now, you're trying to, okay. Now, what I want to basically do is that people realize that this is a very simple model, right? And to like a very good indicator of the complexity of the model or the sophistication of the model is the number of parameters. So we can you just have two parameters, right? So there are just two parameters, and it's probably not you probably cannot fit the entire like complexity of the data with just two parameters. So you increase the parameters in that case. Now, one way to do that is to simply like increase the size of W, but you can't just do that infinitely because you only have certain number of features. Another way to do that is to actually feed the whatever the output you get from this into another linear function like that. So this, for example, is W1. You pass this becomes your new x, and then you pass this to another. Let's say, for example, and then you pass basically that into another linear function, and this again becomes an input to another linear function, and then that comes out as the output. And finally, you get let's say we have now completed 3 layers, right? Now let's say I have 6 parameters, and I'd probably decide that okay, let's say that 6 parameters are now probably enough to fit the complexity of the data set, and that's going to be my final answer. Now, if I'm doing a classification, I'll probably pass it through a torch.sigmoid, and then I'll define my accuracy functions that way. But this is basically the entire concept of a neural network, right? So you guys must have seen this very famous representation of what a neural network looks like. But these are the input features, right? There's blue dots over here. And then you multiply them with your W's, which is represented by these lines, right? And whenever you multiply these with your W's, you basically get some values again, and then you again, which is these black values over here. And then you again gonna multiply them with something, and then you again gonna multiply them with something, and you're gonna multiply them with something. And so finally you're gonna get certain values, which is gonna be a final answer. So that basically is your your neural network model. And now you probably can see how neural network models are nothing but extensions of your normal linear regression models. There's one small caveat to this, which is purely mathematical in nature, is that this actually, if you think about it, you have certain x, and then you pass it through a linear function, then you pass it through another linear function of W2 and B2, and then you pass it through another linear function. Problem with linear function is that let's say I define linear function as fx. Now, f of x is again nothing but another linear function, which is f dash x, let's say, for example. And so you've not essentially increased the complexity of the model. In a sense, you still have just 2 parameters, which is that 1w and 1b. If you want to see how that looks like, what if I expand this function over here? This is going to be nothing but w3, w2, w1x plus w3, w2, b1 plus w3 b2 plus b3, right? Now these are nothing but constants. So this is nothing but one big wx plus b. So you've not essentially changed the complexity of the model, right? Which is why you actually have to introduce some sort of non-linearities within this linear function in order to offset this. So here's what people do. Whatever output you get through this, you're going to pass it through some sort of non-linearity, which I'm going to name as A. All right. And for simplicity's sake, I'm just going to, actually, let me just write it separately. Whenever I first get after this first layer of mine, what I'm going to do is I'm going to probably name this as Y1. All right. Y2 is going to be nothing but W2 times A times Y1 and not Y1 itself. That's B2. And then so on and so forth. Y3 is going to be W3 times AY2 plus B3. What is this exactly A function, right? A is nothing but a non-linear function. Any function that is not a linear function. Apparently, it works very well. For the most part, people actually use this function known as a ReLU function. ReLU function, which stands for rectified linear unit. And this rectified linear unit is basically, I mean, the mathematical definition of ReLU function is ReLU x equal to max comma 0, which basically looks something like this. This is the ReLU function, which is basically the function y is equal to x for x greater than 0 and y is equal to 0 for x less than 0. I mean, you might say that this is basically, for the most part, this is a linear function. I mean, you can see that these are basically two straight lines that are joined together, but it's still a non-linear function if you think about it. And people have actually found that even such a basic non-linear function works very well. So that is basically what we're going to be doing. All right, let's define our models over here. But before I do that, let's see what exactly I'm going to have to do. So I'm going to define my the MLP model over here, which I'm going to be defining in the form of classes now and not functions anymore, because it's a better way to write code, simply put. And also, PyTorch can handle classes much better than functions itself, because classes have methods in them that you can use to, do different a class itself can be a home to different functions. And so you can actually package different functions into one. So for example, my neural network model, and then my function which calculates the model, and then the function which calculates the gradients, all can be packaged into one particular class, and it's going to come very handy to me. And that is why I'm actually going to be refactoring this. If you're not clear with how classes work or how, I recommend you look at the very first lab 0, which I recorded. It's put on the website. Each class has a def in it, which is a function that is run when you initialize a class to a particular variable. So it's going to take two variables, that is n in and n out. And what exactly is n in and n out? If you remember this neural network function, it took in certain features. So let's say for my x was, let's say for example, had 3 features. Let's say age, sex, and ticket fare, for example. So my n in is going to be number of inputs I'm going to have, and n out is what's the actual last value, number of values that you want. In our case, we just want one value, which is going to be a value from 0 to 1, which we're going to be using for classification of whether the person has survived or not. Oh, but in this case, since you're doing an MNIST classification problem, so my input is going to be like all the pixels that you have within your image, which is going to be 1 times 28 times 28. And my output is going to be 10 different values from 0 to 10. And we're going to look at how we're going to handle that. Whenever you're defining a neural network model, always make it inherit from nn.module, which contains a lot of stuff related to neural network models, which you almost always should do. I mean, I'm going to talk about why exactly this is, but just remember this as a thumb of rule. And whenever you're using nn.module has certain functionalities that you want to initialize. So what I'm going to do is that I'm going to do super.init, which is basically going to be run the initialization of nn.module within this initialization function as well. I'm going to be now in this neural network model, these things over here that you see over here, this orange, green, 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 these individually are called layers of the function. Now, layers are nothing but different weights and biases. So for example, layer number 1 is going to basically contain this W1 and B1. And when I'm passing my X through that layer 1, I'm basically, what I mean is that I'm multiplying my X with W1 and B1. Now, W1, B1 this time will not be one single value because I'm going to make sure that my W is in such a way that I have another tensor now. And let's say now my tensor is of size 10, right? I'm going to pass it through layer 2, which is going to be W2 and B2, and then I'm going to pass it through layer 3, and then finally I'm going to pass it through a sigmoid. I'm going to get some values, and I'm going to get certain values. All right. Okay, should I stop over here? All right, we'll stop over here, and we'll continue with multi-layer perceptrons in the next lab. But hopefully you have now a basic idea about like what exactly neural networks are, and like what exactly is the motivation behind neural networks and how do you build them. So here's something that I wanted to do next time is take first of all, revise lab 1 and whatever we've done in lab 2 till now, and take a look at what exactly neural networks are. Right? And then next time we're actually going to see how to build your neural networks in code, how to design the optimization code. We're also going to look at some really cool object-oriented programming concepts, like how do you refactor your code into classes and then classes of classes, and then how to deal with objects, and that's going to be pretty interesting. And essentially what we're trying to do over here is sort of build an API or sort of build, like, let's say, reproducible code. And you would see that I'm always, defining different functions and different classes and not, writing code on paper. So I'm not basically writing specialized code for given the problem that I have. It's because I want it to be flexible. You can simply replace the data with MNIST, and you shouldn't have to like rewrite all the code related to the processing and then how you feed to the data. So I'm trying to build sort of an API which is highly flexible for all sorts of purposes that you're going to be using. We'll slowly head towards that. So let's stop over here, and I'll see you guys next week. All right, thank you. I'll stay over here if you guys have any doubts.